19th International Physics Olympiad, year 1988. IPHO. Problem 1. Spectroscopy of particle velocities. Theory. Basic data. The absorption and emission of a photon is a reversible process. A good example is to be found in the excitation of an atom from the ground state to a higher energy state, and the atom's subsequent return to the ground state. In such a case we may detect the absorption of a photon from the phenomenon of spontaneous emission or fluorescence. Some of the more modern instrumentation make use of this principle to identify atoms, and also to measure or calculate the value of the velocity in the velocity spectrum of the electron beam. In an idealized experiment, see figure 19.1, a single charged ion travels in the opposite direction to light from a laser source with velocity v. The wavelength of light from the laser source is adjustable. An ion with velocity 0 can be excited to a higher energy state by the application of laser light having a wavelength of lambda equals 600 nanometers. If we excite a moving ion, our knowledge on Doppler's effect tells us that we need to apply laser light of a wavelength other than a value given above. There is given a velocity spectrum embracing velocity magnitude from v1 equals 0 m s to v2 equals 6000 m s. See figure 19.1. Questions 1. Part 1. What range of wavelength of the laser beam must be used to excite ions of all velocities in the velocity spectrum given above? Part 2. A rigorous analysis of the problem calls for application of the principle from the theory of special relativity v prime equal v by square root from 1 plus v over c divided by 1 minus v over c. Determine the error when the classical formula for Doppler's effect is used to solve the problem. Question 2. Assuming the ions are accelerated by a potential u before excited by the laser beam, determine the relationship between the width of the velocity spectrum of the ion beam and the accelerating potential. Does the accelerating voltage increase or decrease the velocity spectrum width? Question 3. Each ion has the value E over m equal 4 by 10 power 6 ampere seconds over kilogram. Two energy levels corresponding to wavelength lambda 1 equals 600 nanometers and wavelength lambda 2 equals lambda 1 plus 10 power negative 3 nanometers. Show that lights of the two wavelengths used to excite ions overlap when no accelerating potential is applied. Can accelerating voltage be used to separate the two spectra of laser light used to excite ions so that they no longer overlap? If the answer is positive, calculate the minimum value of the voltage required. Solution. Question 1. Part 1. Let v be the velocity of the ion towards the laser source relative to the laser source. Nu prime the frequency of the laser light is observed by the observer moving with the ion. For example, in the frame in which the velocity of the ion is 0, and nu the frequency of the laser light is observed by the observer at rest with respect to the laser source. Classical formula for Doppler's effect is given as nu prime equal nu by 1 plus v over c, formula 1. Let nu star be the frequency absorbed by an ion, characteristic of individual ions, and nu L be the frequency of the laser light used to excite an ion at rest, hence, nu star equal nu L. For a moving ion, the frequency used to excite ions must be lower than nu star. Let nu H be the frequency used to excite the moving ion. When no accelerating voltage is applied, we have next table. Here nu L less than nu H, nu L equal nu star. Calculation of frequency nu H absorbed by moving ions represented in formula 2. The difference in the values of the frequency absorbed by the stationary ion, and the ion moving with the velocity v delta nu equal nu H minus nu L. The difference in the values of the wavelengths absorbed by the stationary ion and the ion, moving with the velocity v delta lambda equal lambda L minus lambda H, which is using formula 2. We have v over nu star. Higher frequency implies shorter wavelength, and in this case we have lambda L minus lambda H equal 12 by 10 power negative 3 nanometers. This is the solution to question 1 part 1. Part 2. The formula for calculation of nu prime, as observed by the observer moving towards light source, based on the principle of the theory of special relativity, nu prime equal nu multiplied by square root, from 1 plus v over c divided by 1 minus v over c, where v is the equal magnitude of the velocity of the observer towards the light source. Nu prime is the frequency absorbed by the ion moving with the velocity v towards the light source, also observed by the observer moving with velocity v towards the laser source, and nu is the frequency of laser light as observed by an observer at rest. To put in a metaphoric way, the moving ion sees the laser light of frequency nu even though the scientist who operates the laser source insists that he is sending a laser beam of frequency nu. So nu prime is equal expression 1 and finally 2. The second term in the brackets represents the error if the classical formula for Doppler S effect is employed. So we see that V over C equal to by 10 power negative 5. And finally we have expression 3. The error in the application of classical formula for Doppler S effect, however, is of the order the factor 2 by 10 power negative 10. This means that classical formula for Doppler S effect can be used to analyze the problem without losing accuracy. That was solution to part 2 of question 1. Question 2. When acceleration voltage is used, we have lowest limit of the kinetic energy of ions is 1/2 mvl square, which is equal the charge of electron, E multiplied by U and VL equals square root from 2U over m. Highest limit of the kinetic energy of ions 1/2 mvh square, which is equal to 1/2 mv square, plus charge of electron E multiplied by U, and VH equals square root from V square, plus 2U over m. Spectrum width of velocity spectrum VH minus VL equal expression 3. Note that the final velocity of accelerated ions is not the sum of V and square root from 2U over m as velocity changes with time. In equation 3, if this square root is negligibly small, the change in the width of the spectrum is negligible. By the same token of argument, if this root is large or approaches infinity, the width of the spectrum of the light used in exciting the ions becomes increasingly narrow and approaches 0. That was solution to question 2. Question 3. Given two energy levels of the ion, corresponding to wavelength, lambda 1 equals 600 nanometers and lambda 2 equals 600 plus 10 power negative 2 nanometers. For the sake of simplicity, the following sign notations will be adopted. The superscript in the bracket indicates energy level 1 or 2, as the case may be. The sign prime above denotes the case when accelerating voltage is applied, and also the subscripts H and L apply to absorbed frequencies, and also wavelengths, correspond to the high velocity and low velocity ends of the velocity spectrum of the ion beam respectively. The subscript following lambda, or nu, can be either 1 or 2, with number 1 corresponding to lowest velocity of the ion, and number to the highest velocity of the ion. When no accelerating voltage is applied, the subscript 1 implies that minimum velocity of the ion is 0, and the highest velocity of the ion is 6,000 meters per second. If accelerating voltage U is applied, number 1 indicates that the wavelength of laser light pertains to the ion of lowest velocity, and number 2 indicates the ion of the highest velocity. Finally, the sign star indicates the value of the wavelength, lambda star, or frequency, nu star, absorbed by the ion, characteristic absorbed frequency, when no accelerating voltage is applied. For the first energy level we have next table. Differences in frequencies of laser light used to excite ions is nu H1 minus nu L1. Differences of wavelengths of laser light used to excite ions is lambda L1 minus lambda H1. This gives V over nu L1 star equals 0.012. Hence the spectra of laser light, absorption spectrum, used to excite an ion at two energy levels overlap as shown in figure 19.4. When accelerating voltage is applied, let lambda H1 prime and lambda L1 prime be the range of the wavelengths used to excite ions in the first energy level. When accelerating voltage is applied, note the prime sign to denote the situation in which the accelerating voltage is used, and let lambda H2 prime and lambda L2 prime represent the range of the wavelengths used to excite ions in the second energy level also. When an accelerating voltage is applied, condition for the two spectra not to overlap, lambda H2 prime equal or greater than lambda L1 prime. See figure 19.4. Expression 4. Keep in mind that lower energy means longer wavelengths and vice versa. From condition 3 we have lambda L minus lambda H equal V over nu star. Expression 5, lambda Ln prime minus lambda Hn prime. The meanings of this equation is if the velocity of the ion is V, the wavelength which the ion sees is lambda L, when lambda H is the wavelength which the ion of zero velocity sees. Expression 5, lambda Ln prime minus lambda Hn prime. The meanings of this equation is if the velocity of the ion is V, the wavelength which the ion sees, is lambda L, when lambda h is the wavelength which the ion of zero velocity sees. Equation 5 may be rewritten in the context of the applications of accelerating voltage in order for the two spectra of laser light will not overlap as follows, where n is the order of the energy level. Expression 6. The subscript L relates lambda to lowest velocity of the ion which sees, frequency nu star. The lowest velocity in this case is square root from 2 EEU over m, and the subscript h relates lambda to the highest velocity of the ion, in this case is square root from v square plus 2 EEU over m. Equation 6 will be used first to calculate width of velocity spectrum of the ion accelerated by voltage u, and second, to calculate potential u, which results in condition given by expression 4. Let us take up the second energy level, lower energy level of the two ones, of the ion first, lambda L to prime minus lambda h to equal v prime over v star. Expression 7 substitute v prime equals square root from 2 EEU over m, lambda h1 equals 600 plus 10 power negative 3 nanometers. V star equal 5 by 10 power 14 Hz, v equals 0 meters per second. So lambda h to prime equals 600 plus 0.001, multiplied by 10 power negative 9 plus square root, from 2 EEU over m divided by 5 by 10 power 14 meters. Expression 8. Considering the first energy level of the ion lambda L1 prime, minus lambda h1 equal v prime over v star. Expression 9. In this case v prime equals square root from v square, plus 2 EEU over m, v star equal 5 by 10 power 14 Hz, v equals 6000 meters per second, lambda h1 equals 600 by 10 power negative 9, and lambda L1 prime equals 600 by 10 power negative 9 plus square root, from 2 EEU over m divided by 5 by 10 power 14 meters. Expression 10. Substitute lambda h2 prime from 8 and lambda L1 prime from 10 in for 1, gets inequality 11. Which means 500 greater or equal to expression 12 or expression 13. Assume that u is of the order of 100 and over, then we have next calculations. And finally we have u greater or equal 162 volts. The minimum value of accelerating voltage to avoid overlapping of absorption spectra is approximately 162 volts. That was solution to question 3. This concludes our discussion of the solution to problem number 1 at this Olympiad. The 19th International Physics Olympiad Year 1988 IPHO. Problem 1. Maxwell's Wheel. Theory. Introduction. A cylindrical wheel of uniform density, having the mass m equals 0.4 kilogram, the radius r equals 0.06 meters, and the thickness d equals 0.01 meter is suspended by means of two light strings of the same length from the ceiling. Each string is wound around the axle of the wheel. Like the strings, the mass of the axle is negligible. When the wheel is turned manually, the strings are wound up until the center of mass is raised 1 meter above the floor. If the wheel is allowed to move downward vertically under the pulling force of the gravity, the strings are unwound to the full length of the strings, and the wheel reaches the lowest point. The strings then begin to wound in the opposite sense, resulting in the wheel being raised upwards. Analyze and answer the following questions, assuming that the strings are in vertical position, and the points where the strings touch the axle are directly below their respective suspending points. See figure 19.5. Questions. Question 1. Determine the angular speed of the wheel when the center of mass of the wheel covers the vertical distance s. Question 2. Determine the kinetic energy of the linear motion of the center of mass, e, r, after the wheel travels a distance s equals 0.5 meters, and calculate the ratio between e, r, and the energy in any other form, in this problem up to this point. Radius of the axle equals 0.003 meters. Question 3. Determine the tension in the string while the wheel is moving downward. Question 4. Calculate the angular speed omega prime as a function of the angle phi when the strings begin to unwind themselves in opposite sense, as depicted in figure 19.6. Sketch a graph of variables, which describe the motion, in Cartesian system, which suits the problem, and also the speed of the center of mass, as a function of phi. Question 5. If the string can withstand a maximum tension Tm equals 10 newtons, find the maximum length of the string which may be unwound without breaking by the wheel. Solution to problem number 2. Solution to question 1. In this problem, it is easiest way to use the formula for the law of conservation of energy when the center of gravity of the wheel is lowered by a distance s. Its potential energy is converted into kinetic energy of translational motion plus rotational motion. That is, formula 1 is true. Next, we note that the moment of inertia round the center of mass I for the wheel is equal to m r large squared, and the kinematic condition linking translational and rotational motion gives the ratio v equals omega r small. Substituting these two expressions into formula 1, we obtain formula 2, where omega is calculated by formula 3 and is equal to 52.1 radian per second. This was the solution to question 1. Solution to question 2. The kinetic energy of linear motion is given by formula 4, which, when converted to known and calculated variables, gives 4.9 by 10 power negative 3 of a joule. The kinetic energy of rotational motion is given by formula 5. Thus, the ratio of the kinetic energies of linear and rotational motion, after simplifications, is equal to the ratio of the squares of the inner and outer radii. Formula 6. This was the solution to question 2. Solution to question 3. In question 2, we found out how angular velocity depends on the distance traveled. This was formula 6. Rewritten it here, omega is equal to the following expression. Then the linear velocity downwards v will be omega by r small, and v squared will be expression 7. But on the other hand, v squared is equal to 2 by a by s. Formula 8. From this we get expression 9 for the linear acceleration downwards. This is formula 9. Newton's second law through the formula 10m by a equals mg minus 2t gives us the final answer for the tension of one of the two threads in expression 11. This will be 1.96 newtons. This was the solution to question 3. Solution to question 4. After the entire length of the threads has been completely unwound, the wheel continues to rotate about the point O, which is at rest for some interval that will be discussed. Let omega be the angular velocity of the center of mass, about the axis passing through the point O. And the angle phi is measured from the horizontal, as shown in figure 19.7. Then from the law of conservation of energy we have formula 12. Here Ia is the moment of inertia about the point O. Formula 13. It follows that omega is expressed as a function of the angle phi through formula 14. To plot the angular velocity omega versus angle phi, note that r small is much smaller than the height h. Thus, formula 14 with a known approximation is transformed into 15, which is a shifted sinusoid. Figure 19.8. The velocity of the center of mass is calculated accordingly by the formula r small by omega, which leads to formula 16. This was the solution to question 4. Solution to question 5. It is obvious that the maximum tension of the threads will be in the position when the center of mass is at the lowest point directly under the axis O. There, both omega is maximum, and the force of gravity, with the centripetal force, are directed strictly vertically. Thus, Newton's second law gives the expression to Tm is equal to mg, plus m omega squared by r small. Formula 17. From which we obtain formula 18. From here, the maximum length h is calculated by formula 19, and is equal to 4 94 of a meter. This was the solution to question 5, and here we finished discussing problem 2. 19th International Physics Olympiad, 1988 year. IPH. Problem 3. Recombination of positive and negative ions in ionized gas. Theory. Introduction. A gas consists of positive ions of some element, at high temperature, and electrons. The positive ion belongs to an atom of unknown mass number Z. It is known that this ion has only one electron in the shell, orbit. Let this ion be represented by the symbol as Z-1+. Constants are given that may be useful later. Question 1. Assume that the ion which has just one electron left the shell, a Z-1+, is in the ground state, in the lowest energy state. The square of the average distance of the electron from the nucleus, or a square with components along x, y and z axis being delta x square, delta y square, delta z square respectively, and r0 square equal delta x square, plus delta y square plus delta z square. and also the square of the average momentum by p0 square equal delta px square plus delta py square plus delta pz square, whereas delta px greater or equal Planck constant over to delta x, delta py greater or equal Planck constant over to delta y, delta pz greater or equal Planck constant over to delta z. Write inequality involving p0 square multiplied by r0 square in a complete form. Question 2. The ion represented by AAZ-1 plus may capture an additional electron, and consequently emits a photon. Write down an equation which is to be used for calculation the frequency of an emitted photon.
Question 3. Calculate the energy of the ion Az-1 plus using the value of the lowest energy. The calculation should be approximated based on the following principles. 3a. The potential energy of the ion should be expressed in terms of the average value of 1 over r. That is 1 over r0, where r0 is given in the problem. 3b. In calculating the kinetic energy of the ion, use the average value of the square of the momentum given in 3.1 after being simplified by p0 square r0 square approximately equal Planck constant square. Question 4. Calculate the energy of the ion Az-2 plus taken to be in the ground state, using the same principle as the calculation of the energy of Az-1 plus. Given the average distance of each of the two electrons in the outermost shell, same as R0 given in 3.3, denoted by R1 and R2, assume the average distance between the two electrons is given by R1 plus R2 and the average value of the square of the momentum of each electron obeys the principle of uncertainty. That is P1 square R1 square approximately equal Planck constant square and P2 square R2 square approximately equal Planck constant square. Hint: make use of the information that in the ground state R1 equal R2. Question 5. Consider in particular the ion Az-2 plus is at rest in the ground state when capturing an additional electron and the captured electron is also at rest prior to the capturing. Determine the numerical value of Z if the frequency of the emitted photon accompanying electron capturing is 2.057 multiplied by 10 power 17 radians per second. Identify the element which gives rise to the ion. Solution to question 1. According to the condition for coordinates R0 and momentum P0, we have the following relations. Since the uncertainty principle holds for momenta the following inequalities, we have the following inequality for expressing P0. Due to symmetry, the following relations hold for coordinates. Substituting them into the previous formula yields the following inequality. P0 squared R0 squared is greater than or equal to 9/4 of Planck's constant squared. This was the solution to question 1. Solution to question 2. Let VE is the velocity of the outer electron before capture. VI is the velocity of Az-1 plus before capture. Vf is the velocity of Az-1 plus after capture. hν is the energy of the emitted photon. Then the law of conservation of energy gives equation 1. Here EAZ-1 plus and EAZ-2 plus denote the energy of the electron in the outermost shell of the ions Az-1 plus and Az-2 plus respectively. The law of conservation of momentum gives equation 2. Here vector 1 is the unit vector indicating the direction of motion of the emitted photon. Thus, the equation that will be used to calculate the frequency of the emitted photon is given by formula 2. This was the solution to question 2. Solution to question 3. Definition of energy Az-1 plus. Potential and kinetic energy are defined by the following expressions. If the motion of electrons is limited to the xy plane, the uncertainty principles of 3.1 can be written as follows. Hence P0 squared is equal to the following expression. which gives P0 squared or 0 squared is equal to h squared. Formula 3. That is, the total energy is equal to the following expression using Formula 3. The minimum energy exists when the first derivative with respect to R0 is equal to 0. Hence we have the following expression. Hence 1 over R0 is equal to the expression 4. This gives the following expression for energy. Formula 5. This was the solution to question 3. Solution to question 4. In the case of Az-1 plus ion captures a second electron, potential and kinetic energy of both electrons are next one. Potential energy due to interaction between the two electrons is this one. So total energy is in expression 6. Total energy is lowest when first derivative is 0. It means that after 6 we have expression 7. And 1 over R0 equal expression 8. Finally, total energy of the ion Az-2 plus is in expression 9. That was solution to question 4. Solution to question 5. The ion Az-1 is at rest when it captures the second electron, also at rest before capturing. From the information provided in the problem, the frequency of the photon emitted is given by this expression. The energy equation can be simplified to expression 10. Using previous results we will get expression 11. Putting in known numbers follows equation 12, which can be simplified to 13. With the physical sensuous Z is 4.1. Expression 14. This implies Z equals 4, and that means beryllium. That was solution to question 5. So we discussed all 5 questions to problem 3.